Cool. Well, let's talk today about learning. So we are done with stuff from the 90s and we are in the 2020s now. Exciting. But today we're gonna talk about learning. Specifically, we're gonna talk about imitation learning. So just to kind of recap what we've done, we talked about state estimation, we've talked about control, about planning, and how these three components can form the elements of a model-based control system, like you have been seeing on your stars, right? So all the projects are completely model-based. Maybe next year we'll introduce a learning one. But you talked of you're going to put together the three pieces for your final project. Yeah.
Just for my clarification, so model-based is basically programmed in, they'll never deviate from that. Learning is like updating the models, basically.
In a way, I think model-based assumes that you know a physics model of the world. And so like you know how like physics works in your race car, and you use that to do like planning, or use that to do control. Whereas in learning-based things, typically you don't assume that is known. And so you're trying to use data to get over the step. And so I'll go to that. Okay, some logistics. Homework 4 is now out. I think it's due on the 28th. I think, homework 1. There'll be one paper presentation from R2D2, I think, or one of the teams on Feb 26th, on lazy planning. And we have guest lecture 1, which is moved to March 1st, actually, not Feb 28th. So guest lecture 1 will be moved to March 1st. So I'll update that, but those are logistics. Any other questions or concerns? Yeah. I figured I'd post it after the second paper was out. Like the second paper from planning will be on Feb 26th, and I'll just post it after. Cool. All right. So that's logistics. And so let's kind of recap what we've done. We've thought about how to build a model-based system to go from sensors to actuators. We did this using this world model or simulator, right? And then we try to plug things into the simulator, by doing state estimation, figure out where we are, planning to figure out global course paths, and control to follow these paths under disturbances, right? So this is great for lots of problems, right? So are we done? Are we, why do we need any of this learning stuff? So the typical model-based control system for robotics is a pipeline modular system, right? You have different models. This is estimating what state is. This is estimating what paths and controllers are. And this is like actuating the robot, right? So you have different models. Each module is constructed separately. But what you're going to do in an end-to-end learning system is that you're going to like obliterate this whole model, and you're going to try and have a single thing that takes in perception, or something that looks like perception, and output control. And so the whole point is that you're going to use the magic of machine learning and data and function approximation to kind of skip over these modular components and try to use data to go from perception to action. So there's a little more nuance to this. You often have to choose what is your definition of action and what is your definition of perception. Right. So for instance, you can choose to go from like RGB images to currents on your motors. So you typically don't do that. In typical machine learning systems, you like go from some process point clouds or something to something that looks like set points for a PID control. So often it's not that you throw away everything that you've learned, but you choose which parts of the system you're going to replace with learning. So for instance, it might be hard to do modeling and predictions. You might want to replace that with the data-driven thing. So if someone says end-to-end learning, you are replacing parts of your modular system with the learned thing, but don't think of it like just a blind replacement. You have to be careful about choosing your interfaces. Okay, so the idea of learning-based systems is rather than using predefined knowledge about your world, you're instead going to use data to kind of replace those. You're going to try and learn predictive models that are going to take in your observations and produce actions. Right? So why might we want to do this or not want to do this? Right? So we went over this at the start of in our first lecture, if you remember. But the nice thing about an end-to-end system, the nice thing about an end-to-end system is that because you're not designing the modules separately. The modules can like the end-to-end system can compensate for errors in the model. You don't have to hand design the interfaces that go between things, right? And often you find that an end-to-end system tends to work better in the limit of infinite data than a modular system. Because everything is targeted towards the final objective, rather than having these models that are not targeted towards the final objective. And so the errors might propagate in a weird way. On the other hand, with an end-to-end model, you often have a lack of interpretability, a big, I guess, internet, you have ChatGPT or whatever, giving you actions. I don't know what's going on inside. So there's lack of interpretability. Perhaps more importantly, there's lack of reusability. And so if I wanted to change my task, for instance, in a modular system, I have the same state estimation module, but I can change the control module or change the planning module. Whereas in a fully end-to-end system, if I go from perception to action, it's much harder to change what I want to do. And so because of the lack of modularity, you have lack of reusability. And as you use bigger and bigger machine learning models, they often become data inefficient. And that's particularly problematic for robotics because data is not cheap in robotics. And there's no like internet scale robotics data that we really have. Right? And so that becomes a big problem. We will talk about that a little bit today. Does that make sense? Like for why we should think about learning? Like don't be, one thing I want to urge you to do is don't go on Twitter and look at all the learning things and be like sold on learning instantly. You want to think about when and where you should use learning. Like most of industry doesn't use learning for a reason. Okay. So learning is going to be good, but we just need to be careful about where it's going. So the structure of our lecture today is we're going to start by thinking about a formalism for sequential decision making, right? We're then going to instantiate sequential decision making into learning from expert data in a framework we're going to call imitation learning. We're going to study the simplest variant of imitation learning, which is behavior cloning. For behavior cloning, we're going to study what the problems in behavior cloning are, why that's maybe not a great idea, and then we'll think about how to improve it. So that's going to be the structure of our lecture today. Okay, let's keep going. Okay, so let's think about we need a formalism to define learning problems, right? Unlike supervised learning, unlike classification or regression problems, you're doing sequential decision making, right? So which means that you're in this kind of Markov, this thing is called a Markov decision process, but it looks like a Markov chain where you're experiencing a state of the world, you're deciding an action to take, the environment is transitioning to a new state, providing you some reward or cost that's telling you how good or bad you're doing, and this repeats over, right? So the point here is that you're in a sequential decision, and it's not just a one-step process. You don't just output the correct answer. Your actions have effect on things in the future, right? And so you have to reason not just like locally optimal, but you have to be globally optimal. And so it's different from typical machine learning problems, but formalism we'll use is states are going to be S, actions are going to be A, rewards are a measure of how good or bad you're doing. They're kind of like costs, but negative costs. Those are going to be R. And then you're going to have transition dynamics, which is going to tell you which states transition to which other states, right? So this is exactly the same as your motion model, or your dynamics model from control, from state estimation. It's the same thing. The only difference in learning-based things is that you don't actually know the structure of this function. You can get samples from it, which means that you can like execute things in the real world, but you don't actually have an analytical form for this transition, right? So the reason it's learning-based and not model-based is because you don't actually know this function, right? You can get data from it, but you don't know it. So you know how we like worked out the formula for how the car moves around? Imagine that car was like an F1 race car, right? You like don't exactly know how to model the system, but you can get data by running the F1. And so we're going to assume we have data from it, but you don't know the structure of it.
Is that why it's data efficient?
Yeah.
Because you have a lot of it, but don't know it.
Well, it's data inefficient often because you have this like these really expressive functions. Like you have an overly general class of functions because you don't know which things are important and which things are not. And so we need a lot of data to separate out the things that are unimportant from the things that are. Okay, so that's going to be our formalism. And we are going to typically operate in a situation where you obey the Markov property. So if you remember Bayesian filtering, same property, right? So in a Markov decision process, it's called a decision process because you can take action in the world. The past is independent of the future, conditional on the present, right? So if you have a joint likelihood of S1, S2, S3, you can break it up into S3 given S2, S2 given S1, and S3. Right? So S3 and S1 are independently of S3. Yep. So that's the Markov property. And then we're going to define a notion of something called a trajectory. And a trajectory is just a sequence of states, actions, and rewards. And so imagine that you like had some strategy to act in the environment. A trajectory is going to be a sequence of I was at this state, I took this action, I got this reward, and moved forward to the next state, next action, next reward. It's a sequence of states, action, and rewards. Yep. So that's going to be our notation for sequential decision making. It's a framework called the Markov decision process. It's like a Markov chain augmented with an action. Okay. So it's important to note that this is a nice formalism to use, but it's one overly general. Like we're not considering this is like overly general because the world has structure in it, and we're like just considering arbitrary. Just the only structure we have the Markov property. And the other thing to remember is that most of the world is actually not Markov. Right, so like your egocentric vision, I turn around, it's not Markov anymore. Because if you have anything with partial observability, the Markov property doesn't hold. Right, so when you want to build practical systems, you want to go beyond the Markov property. But in this class, we're going to think about things under the Markov property, and I'll touch on non-Markov. Okay. So that's our formalism. Let's kind of map it to a real world setting. Right, so let's consider this robot in the kitchen. It needs to put this kettle in the sink. Right, what are states, actions, rewards in this setting? Right. So for instance, states could be something like camera images or joint encoders, things like that, right? Or they could be positions of the objects and joint encoders and tactile force readings, right? All of those would be states. Actions are things like joint torques or velocities or set points for PID controller, right? So you're just choosing the action space, and the action space determines how the world moves forward. You're then going to have your reward would be something like maybe you want to place the kettle in the sink. It's going to be something like the distance from your kettle to your sink or something of that nature. Right? And then your transition dynamics are just going to be physics. It's the real world. So you don't have to like define a model of the real world. You don't know it anyways. The transition dynamics is just going to be physics. You execute those actions in the world will move forward. That's your transition dynamics, right? And so the important thing is we do not assume access to the transition dynamics model. You just assume access to being able to sample from it, which means that you assume that you can act, right? Does this mapping make sense? Okay, so we're just trying to define formalism, right? Once we have formalism, the goal of reinforcement learning is to learn this thing called a policy, right? So a policy 5 has some parameters theta, and essentially you can think of it as a rule book that maps from a state to an action, right? And so what pi theta does is it is a function that takes in a state and outputs an action or a distribution of our actions. And the goal is for you to use experience in the environment to figure out what the best pi theta is. The best pi theta is the thing that accumulates as much reward as possible. Right. So the goal is, let's say you have a stochastic policy, which means that you're going from a state, going through this function pi theta, to produce some actions, but not a single action. You produce a distribution of actions. So let's say you produce the mean and variance of a function. That's a distribution of actions. Or you produce the logits of like categorical distribution. Those are parameters of probability distribution. Right. So you produce a distribution of actions. You want to find the parameters of your function, which maximize the sum of expected rewards under the policy, which means that if you act by sampling from that policy in the world, you're going to maximize the rewards that you get. Right? So let's try and write this out mathematically, and I'll into it after. Right. So mathematically, it looks something like this. It says that you want to learn the parameter theta of your policy, such that if you act according to your policy in the world, you maximize the sum of the rewards that you get. Sometimes this is discounted, you see this gamma to the d, but it doesn't really matter that much. Right? The point is you want to get as much reward as possible. Right? So this is intuitive, it matches like Pavlovian conditioning. You want to, train your brain reflexes so that you get as much, as many treats as possible. The same thing. The important thing you need to define is like, what is this expectation? This is like kind of a weird shorthand. You like probably haven't seen this tau sample from pi theta before. And so let's try to be very concrete about what tau sample from pi theta means. Right. So specifically, when we're thinking about taking the expected reward under a policy, what that means is, let's say you sample your initial state from some initial state distribution. Okay, you had some, let's say you knew that your policy starts in like some initial range. So you sample an initial state. Then you go through this iterative process where you sample an action from the probability distribution that takes in S naught and produces a distribution over action. So like, for instance, the first thing you could do is you take an S naught into your function, your policy phi theta. It outputs the mean and variance of a Gaussian, right? And then you sample from the Gaussian. So what you've done is you sample an initial state, you sample an initial action from your policy, and then you execute your action in the environment, right? Which means that A1 is going to come from the probability distribution of S1 given S naught. So this is just like execute the action in the world, right? And then you repeat. So then you're going to sample, sorry, not A1, S1. You're going to sample A1 from pi theta of A1 given S1. And you repeat, right? So you started at some state, you took an action by feeding it into your policy. Policy gives you a distribution over actions, sample from that distribution, gives you the action. You execute the action in the world, it gives you a new state. You feed that new state back into your policy, you get a new action, and you, right? And the reason it's an expectation is because like these things are stochastic. Your policy is stochastic, your transition dynamics are stochastic, right? So if you remember like the basic lecturing part of our class, everything has to be stochastic to maintain uncertainty, right? And so the world is stochastic, and so this is going to be stochastic, and this is going to be stochastic. That's why it has to be an expectation, right? So the objective of most sequential decision-making problems is to maximize the sum of expected outcomes. Yeah, everyone with me? And the goal is to use data in order to figure out what the parameters are of the policy by data that maps from states to actions. Okay, so let's try and think about why isn't this optimal control, right? We talked about optimal control. We did all this MPC stuff and MPPI, and we talked about LQR and all of like sounded like the same problem, right? So there's some cosmetic differences, and there's some real differences. Right? So the cosmetic differences are those are costs, and this is reward, and that is min, and that is max. Those are cosmetic differences. And oftentimes, optimal control problems are in continuous time, and RL problems are typically in discrete time, or sequential decision-making problems like this are often in discrete time. It means that you have discrete intervals versus a continuous one. But those are like cosmetic differences. They don't really matter that much. The real difference is whether you assume access to the known model, right? Or whether you just assume that you can sample them. So in reinforcement learning, you're going to assume that you don't have access to the models. In optimal control, you assume that you will have access. Right? So for instance, in LQR, you need the gradients of your dynamics. You just don't have that enough. And so that's what makes the method a bit different. Yeah, makes sense? Okay, great. So policies can be of various forms and shapes and types, right? A policy is just a mapping that takes you from states to optimal actions. Right? And so imagine that your states were just like discrete. There was like 50 states in your world, and you can just have a table which tells you, okay, if you're at this state, do this. If you're at this other state, do this. If you're at this other state, do this, right? So the simplest representation is a table. Right? The problem with the table is that the table blows up as your state space blows up. And if you're in if you're in the world, you're never actually at the same state. Like you're there vanishingly small, right? It's a continuous space. And so when you're in continuous space, often you want to learn policies which are linear or non-linear, right? So what I mean by that is that you have some function which takes in an S and has some parameters W that gives you, like, for instance, the mean and variance of a Gaussian. And so you're going to have these like function approximators, or you could have a neural net that takes in state and produces the distribution of it. And so the whole point is that as we get more and more complicated, you can go from a table to a linear setup to a big neural net or a decision tree. You can have like a more and more complicated function approximator. And a function approximator is something that It's a parameterized function that tries to like approximate your mapping from states to actions. Like approximate the optimal mapping from states to actions. Does that make sense? How many of you have done machine learning classes? Some number? Okay. But essentially, in most the premise of machine learning is that you have a data set of x's and y's, and you're trying to learn a parameterized mapping that takes you from x's to y's. Okay? It's kind of the same thing. These are just different forms of the parameters. You may think of. Okay, so that's what a policy is, and the natural question to think about is how do we learn policies? Okay? We want to learn policies. We want to do it in this reinforcement learning framework. And we're going to discuss 3 different ways of doing it. The first is going to be imitation learning, actually, which means that someone is going to provide you expert data or almost expert data, and you're going to try and copy that expert data. Yeah. The second is going to be model-free reinforcement learning, which means that someone is going to give you a reward, and you are going to try and act in the world so that you maximize that. Okay? And the way you're going to do it is you're going to try and do gradient descent on that objective. So essentially, most model-free RL methods look like doing some version of gradient descent on that object. Yeah, it's called optimization maximus. And then model-based RL is a little bit different. What model-based RL does is it tries to take data from the world. It tries to approximate how the world works, right? So we talked about a world model in all the lectures before. What model-based RL does, it tries to take data. It tries to, rather than trying to approximate a policy, which maps from state to action, it tries to approximate a world model that maps from state, action to next state. So it tries to approximate a function that can figure out how the world works, right? And then I use that approximated thing to then figure out how that works. Okay? So you can reuse all the machinery we did earlier in the class. You're just going to not assume that the model came from a human, you're going to get it from data. Yeah. So I'm sure you all have seen this OpenAI Sora thing that came out recently, right? Like they're claiming that they're essentially getting a model, and then you can use the model for things like planning or control, because it's an approximation of how the world works that they got from Google, right? And so the idea of model-based RL is you're going to use data from the environment to model how the world works, and then figure out how to do different tasks in your approximate model. Yes? Okay. So today we're going to specifically focus on imitation learning, which is learning from expert demonstrations. Okay, yeah.
Model-based RL, why are you doing this?
Well,
Model-free.
you're doing gradient descent because that's a maximization problem, right? And so any maximization problem, you can just do gradient descent to maximize it. And so essentially what model-free RL says is that is your optimization problem. Just do the most obvious thing, gradient descent. If you have some maximization problem, you always want to go in the direction of the. Okay, so we're going to start with imitation learning. And any questions before we get into the details of imitation? Okay, so everyone's comfortable with the premise of sequential decision making? Great. So let's speed through the next bunch of things and we'll solve AGI by tomorrow or by Friday. Sorry, I don't want to be too ambitious. So the key idea of imitation learning is that you're given demonstrations of optimal behavior, right? So for instance, if you're doing autonomous driving, someone gives you examples of images and what action you would take, right? So you can have an expert driving around, you record what they saw and what they acted with. That is a data set demonstrating optimal behavior, right? Or if you have a robot, someone is moving the robot arm around in optimal ways or approximately optimal ways. You're going to consider those demonstrations of optimal behavior. And so we're going to assume that you have trajectories of states and actions that are coming from an expert or something that's close to an expert. You don't need to assume rewards in most imitation learning or many imitation learning frameworks. So you're just going to assume you have expert states and expert actions. Right? So you have to assume that they're close to it. Yeah, so if you don't assume they're close to expert, then you often have to go back to some reinforcement learning type frameworks because you just it's an underspecified problem. Okay, and so you're given these demonstrations of optimal behavior, and the goal is to train a policy to mimic the demonstration. Now, question for y'all is why, if I'm giving demonstrations of optimal behavior, why do I need a policy? I already have the optimal behavior. What's the point of adding a policy? But I already have the optimal behavior, so if I like was there, I could just replay the action. Right? But there's another scenario, perfect, yes. So what you need, the reason you need a policy is because you're given state actions in a limited set of, limited set of states. You're given optimal action in a limited set of states, you show up in a new state, you still need to know how to act, right? And so the whole point of learning policies is that it has some generalization to new points. So if you just wanted to copy things in the training things, you don't need a functional approximation. The other caveat is that the world is stochastic often. You're going to have some noise. And so replaying the actions open loop is going to have all the bad issues with open loop control that we talked about in control, right? And so typically what you want is a policy that will act in closed loop, which means the way the policy is going to act is it's going to take in the state, produce an action, the action is going to get executed. You take in the next state, produce an action gets executed. Same loop we did here, right? We're just going to use the expert data to figure out this pi theta. Does that make sense? So the important thing is we have demonstrations of optimal behavior as in trajectories. You're going to train the policy to mimic the demonstrator. And then you're going to like evaluate by running that policy in closed loops, running that policy in this loop right. Everyone with me? Great. So let's do the simplest possible thing, right? Let's treat this as a prediction problem. So let's say, if you've seen how like image classification works, you've taken an image, you try to produce a label as a cat or a dog and everything. It's like the same problem, just a regression problem, right? So you want to say, given demonstrations of optimal behavior, let's say you're given states and actions, S naught, A naught, S1, A1, S2, A2. You want to train a policy to mimic the demonstrator by maximizing likelihood, right? So you want to say, let's treat it as a supervised learning problem. So the supervised learning problem tries to say, you want to learn a model that maximizes the likelihood of the expert data. Right? So it's trying to say that if you're at that state, you would produce the expert action as the most likely action. Right? And so mathematically, you can write out maximum likelihood that looks something like this. It's saying that given a data set of expert demonstrations, you want to sample S star, A star from that data set. And you want to like find the parameters theta such that you maximize log by theta of A star given S star, right? So intuitively, it means that you have a function by theta. It's going to take in your state, produce a distribution or reflection. And you want to find the parameters of that function approximator, which make the expert actions highest likelihood. So the easiest way to understand this is considering it deterministically. Let's forget about probability distribution. Let's say that you had states and actions, right? So if you had states and actions, the easiest thing to do is you want to like find the parameters by theta, which minimize the difference between A star and pi theta of S star, right? So S star, the simplest case, let's say you map from S star to this function to an A hat, right? Let's call this thing A hat. It's like your guess is the best action. You want that best action to be as close as possible to the optimal action, right? And maximum likelihood is just a generalization of that to be probabilistic, right? But it's basically trying to say minimize the loss function or minimize the distance measure, which tries to make the predicted actions close to the expert actions, right? On the states that the expert was in. It's important that you're sampling S star and A star from the expert data, and I'll talk about why that's a problem. And you're trying to maximize the likelihood of A star given S star. Okay, this is not, since we haven't covered machine learning, this might be confusing. So ask me questions, which, like, does this make sense? So let's try and write it out here. Let's try and draw what this means a little more into it. Okay? So I haven't been covered in chalk in a bit. Okay, so you have an S, where S is going to go into, let's say you had like a neural net, right? And your neural net has all of these weights and everything, right? And out is, let's consider the deterministic case, right? What's gonna come out is an A hat, right? And you have some parameters theta. So you're gonna say A hat is equal to, let's call it phi theta of S. Yeah, that is your best guess at what action you should take at state S. Right? And now what you want to do is you want to treat this as a minimization problem, where you say, when you sample states from the replay buffer and actions from the replay buffer, which is like expert actions, yeah, sample expert states and expert actions, you want to minimize the difference between A hat and phi theta, A and phi theta S. And so all this is saying is try to find the parameters of their function approximator that bring your best guess closer to what the expert. And you can make this like probabilistic by trying to say that this is going to output not a scalar, but a Gaussian. Let's say it output a Gaussian. You want to like move the mean of the Gaussian towards the expert, right? So you want to make the expert data maximum. Yeah.
So if the data subset.
The weights of your neural nets, right? So it's gonna be the weights of your neural net, or a decision tree is gonna be like your boundaries for a decision tree. For a linear function, it's gonna be your linear weight. It's gonna be how you parameterize your function. How can you change your. Okay, everyone with me? Great. So you want to treat this as a supervised learning problem. You're just going to optimize that with stochastic gradient descent, right? So you can use PyTorch or TensorFlow or whatever JAX that the kids use nowadays. And all of them are basically just going to help you find the parameters theta, which maximizes likelihood. And so essentially, you know, in image classification, you often would take in a picture of tiger and then produce whether it's a tiger or not, right? In imitation learning, what you're going to do is you're going to take in a picture of the road, and then you're going to try and produce whether you go left or right, right? Or if you want to be continuous, you want to figure out like what is your velocity and what is your direction. And so you're just going to try and do it via maximum likelihood. So the nice thing about this is that it requires minimal assumptions. Like all you need to do is you need to have a function approximator, you need to have a data set, and just maximize that. You don't need any extra machinery. So it's like the absolute easiest thing that you can do. And when the pipeline kind of looks like an expert goes and collects a bunch of data, right? So some expert is driving around collecting state action pairs, right? And those state action pairs are your training data. So state action pairs then go into supervised learning. Supervised learning is just maximizing likelihood, right? On the top, or basically the same thing that I wrote here. And then you get your phi theta and you run your phi theta. And the way you run your phi theta in the world is you take your first observation, get your first action, run that action, get your new observation, run it through your policy, get your next action with you. Does that scheme make sense? Okay, so before we go to why that scheme might be good or bad, let's look at some quick pseudocode that I copied off medium.com for how to do this, right? It's very simple. Like I don't need you to actually understand this. I just want to show you how easy it is. Right? So basically it's like 30 lines. Essentially, the main things to remember are that you are like defining a loss function. So if it's a continuous space, your loss function is the mean squared error, which is that loss function that I wrote there. If it's a discrete space, it's the cross entropy loss. For those of you who do image classification, you can use, it's the same thing as image classification. You're just classifying which action you do. And then all you do is you loop through your data. Right? You loop through your data, you have your action prediction, and then you want to make your action prediction as close as possible to your target. That's it. Right? That's the whole loop. So you can write it tomorrow. It's very easy. And it works surprisingly well. And so that's this idea called behavior cloning. That's the easiest way to do imitation learning. It's not the only way to do imitation learning, but the easiest way to do imitation learning, which means that you have expert states, expert actions, is just treated as a prediction problem. and you try to predict A star from S star, you just do this tiny little loop, right? You define a loss function or a likelihood function, and then you just loop through your data, try to make your action predictions close to your target. That's it. Yeah. Cool. So someone came up with this in 1989, and then they used it to drive this car around back then, right? So the picture that they were using looks like that. In a different time, and they used like a tiny little perceptron thing. And it's actually able to drive, like that is videos of it driving around, right? So some expert drove it around, recorded the images, recorded what controls it took. And then they just did behavior cloning, right? And it was actually very successful. So that is, probably the first instance that we remember. But from there, people are still doing it in 2024. So this is a paper that came out like 2 days ago. And what are they doing? They're collecting a bunch of data. They're wearing these like, because they don't want to deal with embodiment shirts, but they're wearing these gloves with cameras on. Right? And then you do this, and then you have robots that are cleaning your dishes, right? And so it's interesting that we've gone from 1989 to 2024, and we're using the same method, right? So probably that method's pretty good. But there's going to be serious problems with it, which we'll talk about. But this is literally a paper from Stanford 3 days, which does behavior cloning. So very relevant in today's day and age, but very simple idea. Like almost every behavior cloning paper we have is the same thing. But you can see that
this video before in class.
I have.
Well, I've seen this video.
It's been on the internet a while. But if you some interesting things to notice about the video is like it like completes the plate cleaning and then you like add more gunk on it and then it tries it again because the policy is running in closed loop. Right. So it's not like you just execute a sequence of actions, your policy is running in new scenarios like this. Right? So that's the whole point. Okay. So that's exciting. Now I'm going to tell you why it's a terrible idea. So the problem here is that imitation learning is not supervised learning, right? So what I mean by imitation learning is not supervised learning is that if you're classifying a cat, right? It's a one-step process. You take in a cat image and you classify it as a cat and you're done. You're given a positive signal if you got it right, or you're giving a negative signal if you got it wrong. Right? Whereas in imitation learning, what we've done is we actually have a sequential problem. Like you have a problem where you have to act for 100 steps in the world, but we've broken it up into a bunch of one-step like classification problems, right? But the issue is that you're like optimizing for this one-step objective, but you're evaluating on a multi-step objective. Right? And so that's what causes the mismatch. So essentially, our loss function or our objective in imitation learning is doing is doing something that looks like that, right? So it's basically saying we are getting states and actions from the expert data, and then you're trying to maximize likelihood. But the important thing is you're doing it from the expert data. And you're doing it per time step on the expert data, right? Yeah.
Does that mean you have like a dramatic divergence?
Yes, yeah. So we'll walk through that in a second. But the issue is that these are from the expert data. And then you're evaluating your policy by running your policy in the world, right? So you're running your policy, you're sampling it, you're sampling it, you're sampling it, and that is not the same as the data that you collected, right? And so what you have is this phenomenon of compounding error. And compounding error is most easily understood as follows, right? Imagine that you had a starting state, okay? Now the starting state, the expert did this, and you're like almost correct, but you had a little bit of a mistake, right? And now the expert continued to, let's say the expert continued to do this, right? You had a little bit of a mistake, and now you're at a state that was never actually seen in the expert data. It's a little bit different than everything in the expert data, right? And so now you're at a state that's a little bit different, which means that your function is going to be a little bit worse because it's outside your training data. And so now you're going to get a little bit worse here. Now you're further outside your training data, and you're going to get a little bit worse. right? So as you like go for longer and longer and longer, little errors compound. Because it's not just a one-step problem, it's a multi-step problem. Right? And so the issue with behavior cloning as a algorithm is that if you make a tiny little error, you get in a state that is unseen. You might make a bigger error. You get in a state that's more unseen. You might make a bigger error. You get a state that's more unseen, even though your one-step error was really small on the expert states, but it's non-zero. Yeah.
There's no way to add like something for error
Corrections.
correction.
That's what you're gonna do. Okay. Well, yeah. No, that makes no sense. That's great. Yeah, that's exactly what we're gonna do. But basically the issue is when you treat a sequential decision-making problem as a one-step decision-making problem, you're gonna have the issue. And so this is the easiest way to think about it. And this happens in practice too, right? So you see this thing, it like tends to start drifting off, like they stopped it there, but it like tends to start drifting off, and I'll show you more examples of this happen. So when you run behavior cloning for long enough horizons and big enough state spaces, you start to see this like drifting problem. Yeah. It's kind of a similar problem to open loop, like you start drifting, but it's a little more nuanced than that because you're still running the policy closed loop. It's just that you're evaluating it on states that are outside the training distribution. And that's what makes it bad. Everyone follows me? Okay. So is all hope lost? No. Tyler just answered our question. The next thing we're going to do is we're going to figure out how to deal with compounding error, right? So this phenomenon is typically called compounding error, and we're going to figure out how to deal with it. So here's an example of, an algorithm that deals with compounding error and applies things to the real world. So this is from NVIDIA back in 2016. Behavior cloning. So you can see that like it's not great if you just run it behavior cloning. And so it starts to do like behaviors like that are unsafe and are drifting, right? But they did a bunch of learning with a special trick I'll talk about in a second. And then you can start seeing things that actually do work. So there's some examples of it doing late keeping. I don't know if I would trust the system enough to do this kind of thing in 2016, but sorry. Yeah, it's just pretty slow. Yeah, it's going pretty slow. Yeah. But it seems to kind of work, right? So what is the trick that they used here? The trick that they used here is very simple, right? They said that, okay, there's going to be these compounding errors, but let's do a really simple trick. Let's put 3 cameras on the car. You have the front-facing camera, and then you have a left camera, and you have a right camera. And so what you're going to do is you're going to take in 3 images. For the left camera, you're going to like label the action as going to the right. And for the right camera, you're going to label the action as going to the left, right? And then when you run the policy is only going to use the middle camera. But what it means is that just from like one observation, you also have labeled things that are like, if you had been in a position where your car was tilted, you would have seen the observation from the left camera, right? And so basically it says if you had seen the thing on the left, turn right. If you'd seen on the thing that's right, turn left, right? And so what that allows you to do then is it allows you to like correct for any of this drift. So basically it's saying, okay, at this state, let's see, this is what the left camera would see, this is what the right camera would see. Left camera goes right, right camera goes left, right? And so you like correct back to where you want to be. Right. And so that leads to this kind of behavior, right? And so the general principle here is that, okay, you have like compounding error where your trajectories start to deviate as you go further and further, right? And what we're going to try and do is we're going to try and stabilize things. So we're going to try and provide corrections that bring you back to the manifold C. Right? And so the ways to fix compounding error are essentially what Tyler was just saying, you are trying to bring the agent back to things that it's see, right? And so correct for this deviating error. And so that's the general principle. So this is what the compounding error looks like in behavior cloning. You start deviating and you go way further. What you really want to do is you want to provide corrected labels that say, okay, if you were here, come back here, if you were here, come back here, if you were here, come back. So even if you deviated for a little bit, you will come back to the training. Right? And so that's going to be the general principle of the next class of methods, which is essentially trying to say behavior cloning is bad because of this compounding error. It's a fundamental issue. We're going to try and provide these corrective labels that fix this. Yeah? You have a question? No, only that. Okay, so mathematically, what it's saying is that if you have a policy pi theta, right, the thing that you trained with supervised learning, sorry, there we go. Sorry. So pi theta is the thing that you learn, right? And when you executed pi theta in the world, you got this red line. And when you executed or when you ran with the expert perform things, you got p data. Right? So p data is the distribution of states that the expert saw, and p pi theta is the distribution of states that your policy saw. Right? And they're different because of this like compounding error issue. Right? And so what I want to do is take the trick that NVIDIA did in 2016 and make it more general. Okay? So we're going to say that p pi theta and p data are not the same. And that's what's going to cause our problem, right? Essentially, p pi theta is a set of states that the policy has never seen before. It's only been trained on p data. So if it's never seen these states before, it's going to do crazy shit, right? And so the point is, can we try and make p data and p pi theta similar? We want to make p data and p pi theta similar. How do we do it? So what are some ideas to do this?
Say just the action based on the difference between the two.
Just the action of the different two. It's a good idea. In case where you don't have a model, how do you know what actions you bring? Right. So in like if you have a point that can translate in the world, then CSE. So imagine you had like a humanoid. How do you know what actions would bring you back?
I'd say go off of your positive or negative. So like if it's, say if you're positive and you're more this way, then you take a negative action to try to get closer. And
Right.
you can evaluate.
So you can do something like 3ID, like, right? Like essentially like, so that's one way of doing it.
What's those?
It's like state itself. You will often use state and observation interchangeably. So ST and OT are kind of state effect. So yeah, that's definitely one good suggestion, which is like try to do stabilization by like PID control or feedback control. That's a good suggestion. What we're going to do first is actually a little bit different, right? What we're going to do is rather than trying to change p pi theta in a clever way, we are just going to change the data distribution, right? And so what that means is that we're going to introduce this algorithm called Dagger or data set aggregation. It's like dead simple, right? What it's going to say is that you collect some so you start by training your policy pi theta on some state action pairs, observation action pairs. So you train it with supervised learning, same as we did before. Then you're going to run pi theta, right? You run pi theta, you're going to get this deviating thing, right? And you're going to get states that are different from p pi expert. You're going to get p pi theta. But then what you're going to do is you're going to ask a human to take these observations that you got when running p pi theta and label them with expert action. And so all you've done is now your earlier training data was this. Your training data now includes this, but with optimal actions, right? So a human is going to give you the optimal actions that bring you back to where you want to be, right? And so your suggestion was using feedback control, which may work in certain systems, may not work in others. What data set aggregation does is it says relegate that task to the human. Right? So the human, you're going to like train your policy, run your policy on new observations. You're going to ask a human to label it with optimal actions. And then you're going to add that data set to your existing data, retrain and repeat, right? Yeah.
Is that going to push you more towards the middle of that graph rather than right on the line?
So it's not saying that you're going to go, it's not saying that go here. It's saying that at this state, go back to where you wanted to go back to. Yeah, exactly. And so when you apply this in practice, you can get drones that fly around forests and are able to go pretty fast. And so at this point, it's like almost standard practice in imitation learning to be able to use this kind of data set aggregation procedure. Right? And so the idea is very simple. It's saying, run your policy, get your human to relabel things on new states, add it to your data set, repeat. That's it. Yeah. And the whole point is you've brought P data closer to P pi theta. Right? That's the whole premise. Okay. See, this person is outside our door, so we should probably leave. But yeah, thank you.